Hi everyone. Today we're going to continue our discussion on vector spaces. So if I remember correctly, the last thing we talked about was subspaces, and we actually have some example of some basic subspaces in Rn, and then we also realize and have theorem 3.2.3, which state that for Rn all the subspaces would be k-planes. So now today what we're going to talk about would be the following, would be to talk about subspaces of other vector spaces. So our first example will be on continuous functions. So imagine the following. Okay. So let's try an example. So let's say we have the continuous function space from A to B. Let's do a closed domain. Be the vector space of all continuous functions f that map from the domain A to B to the real numbers. So these consider for all continuous function from A to B. So remember, in this case, I'm not talking about function that specifically have a domain that's from A to B, but it could be a function that have a larger domain, so they will obviously be defined from A to B. So meaning in this case, for example, if I talk about, let's say, the domain from 0 to 1, then I'm basically talking about any function that is continuous from 0 to 1. So it could be x squared, could be x, could be sine x, could be cosine x, or could be a lot of other functions. So I'm not restricting the domain, but just need the function to be continuous within that interval. So let's say we let V be the subset of C, the continuous function space from A to B, such that this is true, such that the integral from A to B f of x dx will have to be 0. And what I want you to do is to show that V is a subspace. V is a subspace of this continuous function space. So how does that work? So if you recall from our last video, to prove a subspace is actually not that bad to do, because you're already starting with something that is a vector space. So therefore, a lot of the properties that's already involved would still automatically apply to every element within your subset. The only problem that we have to make sure is that when we reduce the number of elements by forming the subset, we do not screw up the closure property and the zero property, because all the other properties are unaffected by how many elements in the set, okay, except those three. So therefore, that's what we're going to have to do. So how do you prove that this is a subspace? So if you recall, to prove that it's subspace, I need to show the zero elements in the function, in the subspace, and then it has addition closure and scalar closure. So let's see if we can do that. So let's start with the zero element, because that's easy to do. So zero element. So if you recall, the continuous function space, the zero element is z of x equal to 0. So the question is, does z of x equal to 0 satisfy the condition so that it can be in V? So what is the condition? The condition is that integral from A to B of whatever function we choose in V have to equal to 0. So therefore, let's see what happened here. So if I look at an integral from A to B of the function z of x dx, then that would just equal to integral from A to B 0 dx. And that would just be equal to 0 automatically. So therefore, tell me that z of x, so that implies that z of x equal to 0 is within V. The zero function will satisfy the condition set for, so that it will be in the subset of V. So that's good. Next, I have to show addition closure and scalar closure. So to do that, what I'm going to do is I'm going to first define two functions. I'm going to say let function f and function g both in v. So what does that imply? That implies that if I take the integral from a to b f of x dx, I get 0. If I take the integral from a to b g of x dx, I also get 0. Because that's the property of any functions within v, is that when I integrate from a to b, I get 0. So if I have two functions that's in v, then that automatically tell me that both of them, when I take the integral from a to b, I get 0. Now, I know some of you might be thinking, wait, doesn't that mean that these two functions have to be 0 to begin with? Just like what we prove the 0 is in the set? Not true. The reason here, because remember, the integral from a to b f of x dx is what we call the net sign area. So as long as the area over the x-axis balance out the area underneath the x-axis from a to b for the function f, then it could have an integral of 0. So now the question, how do I show? How do I show? If I do have these two functions in v, how do I know that the sum would be in v? So, well, let's see. So what I'm going to show is to show f plus g is in v. So let's figure out what that is. So let's consider f plus g of x. Okay, and what I'm going to do is I'm going to try to take the integral from a to b dx. And so now what I'm going to do is, does that mean the following? So according to function addition, if I have a sum of two functions, I can say that just means those two functions add together. So instead of considered to be one single function, which is sum of f and g, I can say, well, that just means f plus g separately. And because it's inside an integral, therefore allow me to separate into two integrations. And since f and g are both in v, that they both actually just become 0 when I integrate. So therefore tell me that if I do have the sum of these two functions, f and g, and when I integrate it from a to b, I will get 0. And therefore imply that if f and g are in v, then f plus g is also in v, because if f and g are in v, that means the integral from a to b would be 0. Then the sum must also integrate to be equal to 0. Now I can do the same thing for scalar multiple. So if I integrate from a to b some scalar s multiplied by f of x dx, what would happen to it? Well, according to our integration rule, if there's a scalar multiplied by a function inside integral, I can pull the scalar out and integrate the function. And since the integral from a to b f of x dx must equal to 0 if f is in v, then therefore it just becomes s times 0. And guess what? S times 0 is 0. So therefore it say that it means that if f is in v, then sf is also in v. Now, sometimes it's hard to understand what these two statements say. So essentially, this is what it means. So let's see if I can write it out a little differently. So this one basically states the following. If integral from a to b f of x dx is equal to 0, then integral from a to b s times f of x dx must also equal 0. So that's basically what this statement says. And then for this one right here, it say pretty much the same thing. It say if integral from a to b f of x dx is 0, and integral from a to b f of x dx is g of x equal to 0, then the integral from a to b f plus g of x dx must also equal to 0. So those are what we did. So now that we show it must have 0, It has closure for addition. It has additive closure. And also have scalar closure. Closure for, scalar, multiplication. Then therefore tell me that V is a subspace of the continuous function from A to B. All right. Let's see if we can do another example. So let's show you another example with a continuous function. Because if you remember, what we try to work toward is to try to talk about functions as numbers. So that when we solve a differential equation, we have a function as an answer. It won't be so weird, and then we can actually do math with it. So show you another example with a continuous function and subspaces. Example. So once again, let's say we let C from A to B be the continuous function space of all function f that map from A to B to some real numbers. So what I want to do is to define the following. So this one actually is not much showing, but rather presenting argument to argue why it is true. So suppose I define this vector space or subspace. I'm going to define Z with a parentheses 1 on top, A to B. So what does this Z with that with the parentheses 1 mean? So you actually see that notation before. Is we use that for higher degree different derivative. So here I'm going to say C with a parentheses 1, so not like first power, but want to have a parentheses around it. And the reason why, because let this be the set of all continuous function that have continuous first derivative. So this apostrophe, this parentheses 1 is kind of like the first derivative. So we basically talk about the first. So this is usually referred to as the first continuous derivative space. So where we talk about only function that have a continuous first derivative. So what kind of function would be in this set? So for continuous function, you can think of it as, I don't know, sine, cosine, x squared, x, and any function, x to the third, x to the fourth, any of those functions would be considered to be continuous function. But not all of them have a continuous first derivatives. So what could potentially not have a first continuous derivative? So we want something that somehow have a this non-differentiability at some point, but then but still have a derivative everywhere else. So example of that would be following. A very simple example that can come off the top of my head is absolute value function. Absolute value function is a continuous function. So that means absolute value would be, so give you an example. So f of x equal to absolute value of x is an object in the continuous function space because absolute value of x continues from negative infinity to positive infinity. So no matter what we choose a and b to be, the function will be continuous on that interval. But f of x equal to absolute value x is not an object in C parentheses 1, or the first continuous derivative space. So meaning that this statement basically say that absolute value of x, or f of x equal to absolute value of x, is in the continuous function space. But f of x equal to absolute value of x is not in the continuous first derivative function space. So that's an example of function that behave that way. Okay? So now what I want you to do, well, simple. What I want you to do is to show that the continuous derivative space is a subspace of the continuous function space. So meaning that since we know continuous function is a vector space, that I want to show that if I only take element from the continuous function that has continuous derivative, first derivative, they themselves will form a vector space. Now, once again, every property that make continuous function to be a vector space automatically satisfy in the first degree continuous function space. Okay? Why? Well, because every continuous function, if you have a function that has a continuous first derivative, it must be continuous itself. So therefore, if you have a function that has a continuous first derivative, it's automatically in the continuous function space to begin with. So therefore, now what we're going to try to do is simply try to show that if I only take those functions from the continuous function space that has a continuous first derivative, I can still satisfy the closure property for addition, scalar multiplication, and I still have the 0 element within the set. So that's what we try to show. So how are we going to do that? So I'm going to do is I'll give you some time to think about. You can pause the video for a little bit and then try to think about it and then see if you can come up with an idea and then continue the video. So how am I going to do this? Well, I'm going to do it the exact same way as we've done it before. What we're going to try to do is to show three things. First, I have to show that 0 exists in this subspace, and then also have to show that if I take two elements from the continuous derivative space, the first continuous derivative space, they would only form another function that is continuous, has continuous first derivative. So how do we do that? So let's start with the 0 elements. The 0 element. So the 0 element will be the function z of x equal to 0. Okay, so is this in the first continuous function space? Well, let's find out. So if I take the derivative c prime of x, guess what c prime of x is equal to? Well, it's equal to 0. And that is a continuous function. Because z prime of x equal to 0 basically just means a horizontal line that's the x-axis. So therefore, tell me that z of x is within the first derivative continuous space. Okay? So the fact that I'm looking at only continuous functions that have a continuous first derivative, that doesn't exclude 0 from the list, because 0 automatically have all its derivative are 0, and that means they're all continuous, and the function 0 itself is continuous. So now how do I show addition closure and scalar closure? Well, then what I'm going to do is to first define the following. I'm going to let function f, or function f of x, and g of x be in the continuous first derivative space. So what does that imply? That implies that f prime of x and g prime of x are both continuous within its domain from A to B. So now what I want to show, I have to show that if I add these two functions together, they must be continuous. So how do I do that? Well, the same thing as what we did on the last example, technically speaking. So what I'm going to try to do is additive closure. So what I want to do is I want to find out what happens if I take the derivative of the sum. Would the derivative of the sum still be continuous? Okay, so that means, so you can, if you want to write down, you can write down, meaning that if f prime and g prime are continuous, thus f plus g prime is f plus g prime continuous? That's my question. So let's find out. So suppose I'm going to take the function f plus g, so that's the sum, and we'll take the derivative of it, and we'll try to find out if that derivative form a continuous function. So well, let's find out. So that is equal to, because when I add two functions together and form a sum, I can actually separate them into two functions being added together. That's what f plus g of x mean. That's what we define as the function addition. F plus g of x is just f of x plus g of x. And when I take the derivative of f of x plus g of x, I can separate them by taking their own individual derivative. All right. And if I take their own derivative, then what I get would be just f prime of x plus g prime of x. And this is definitely continuous, because both f prime and g prime are continuous, and because sum of continuous functions are continuous themselves. Oh, actually, maybe correct would be to say is the sum of continuous functions is a continuous function. And therefore show that what we have is closure. If you have two continuous functions that have continuous first derivative, if I add them, the first derivative is also continuous. Now, next one would be to show scalar closure. So what does that mean? So that would mean that I have to show, if I multiply either f of g, either f or g by a scalar, I can show that the derivative is still continuous. So let's see. So what I want to do is show what happened to the derivative of some constant. Actually, I think I would use s. S times f prime of x. And I want to know what happened to this thing and see if it's continuous. So I can say, well, that's just the same thing as take the derivative of r s times f of x. Yeah, I don't like this. And based on the way we define scalar multiplication, s times f of x is the same thing as s times f of x. So notice these are properties that we define how scalar multiplication work and how vector addition work for continuous function. So now, because this, according to what we know about derivative, I can pull the s out and just form the derivative of f of x. And so therefore that form s times f prime of x. Now notice that this expression is not the same as this one. Why not? Don't they have like exactly the same thing involved? They have an s, they have an f, they have a prime, then they have a parentheses x. Yes, true. They do have almost everything exactly the same. The difference? This requires us to multiply the function f by s first, then take the derivative. what this statement over here say is I have to take the derivative of f first, then multiply by s. Notice the order operation is different. And yes, you might not think that's a big deal, but it is a big deal in math. Order operation is super important for almost everything. And therefore, there are a lot of properties that allow you to say, well, in this case, you can actually reverse it. That allow us to have more flexibility. So in here, now that I see this, I know this is definitely continuous. How do I know this is continuous? Because, multiply a continuous function by a scalar would result in a continuous function. When you multiply a continuous function by a scalar, you get a continuous function back. So therefore, now show that if you look at the first derivative continuous function space, it has the zero function in it. It has closure for addition. It has closure for scalar multiplication. And therefore, tell me that this is a subspace of this. So the first continuous function, the first continuous derivative function space is the same as, is a subspace of the continuous function space. Now, important to understand what that means. That means that continuous function space is a vector space, and so is the first continuous derivative function space. But the difference is, the first continuous derivative function space is a subspace of the continuous function space, indicating that there are less functions in the first continuous derivative function space than in continuous function space. Which makes sense, because every single function that have a continuous first derivative must be continuous. But there are continuous functions that do not have a continuous first derivative. So therefore show that there will be more continuous function, but less continuous function that also have a continuous first derivative. Now, here comes the interesting part, and some of you are probably already thinking about it. What if I then take the derivative from all the functions that have the continuous first derivative? What will happen? Well, guess what? You form a different subspace. So this is how this whole thing works out. By simply applying the same exact argument, we can define the following subspaces. So we start with our vector space, so that would mean that this is probably the biggest out of this list of vector space. So this is my continuous function space. So that's often referred to as a continuous function space. And that consists of all continuous functions in the form of f of ab mapped to the real numbers. So remember, in this notation, this ab is defined the domain of the function. For more often than not, it will probably be negative infinity to positive infinity for most cases, but it could be something specific. So that is my vector space. So now what happened is I can now define the following subspaces. So these vector space are subset of this continuous function space. So they're all smaller. And they, as a matter of fact, they all continue to get smaller and smaller in each layer as they go down. So next one would be C parentheses 1, square bracket A to B. So that would be the first continuous first derivative function space. And yes, functions that have a continuous first derivative automatically continuous. So therefore, every element in this set will have to be in here. But there are some in here that are not in here. That's the reason why this is a subspace of this one. And so this basically consists of all function that has continuous first derivative. Okay? And then I can then define a C parenthesis 2. So what do we call this one? Well, guess what? This one is called continuous second derivative function space. That means these are all functions with continuous second derivatives. And now when I say that, important to understand is the following. If a function have a continuous second derivative, it must have a continuous first derivative for it to work. And if a function have a continuous first derivative, it must be continuous. So therefore, by stating they have a continuous second derivative, it automatically forces it to satisfy both continuous first derivative and continuous at the same time. And because now that this one have basically 3 requirements. See, the continuous function space have 1 requirement, continuous. Continuous first derivative function space have 2 requirements, continuous function, continuous first derivative. Okay, and so now this one have 3 requirements. Therefore, the function now should have a smaller list than before. And we can continue this process to define the C parentheses n square bracket A to B. And that defined to be continuous nth derivatives function space. And these are all referred to as subspaces of the continuous function space. Now, is that all the subspaces for the continuous function space? No, continuous function space, because have infinite number of elements in it, and they are literally infinite variation of function that we can talk about. It has a lot of different subspaces, and this list is just the subspaces that are relating to derivative. And why do we care about that? Well, because we're doing differential equation, and differential equation basically talk about derivatives. So we want to talk about functions that have a continuous derivative, so that when I put them in a differential equation, I can actually find the derivative to show that they are actually can be used to fulfill what the equation is. So that's the reason why we're interested in these continuous derivative function space. All right. Now, unfortunately, my video is 34 minutes already, so I'm going to stop right here. I want to have a little bit more to talk to you about in for vector space, so I would talk to you about the last thing tomorrow. I really don't want to squeeze that into this video because that would be like another 10 minutes or more. So I think that would be too long. So we can have a short video for tomorrow. Okay? All right. Talk to you guys tomorrow. Bye.